Welcome back. So next I want to talk about TummyFlex's play-in agent. So again, the challenge that this is trying to address is that we might have some modified, for instance, optimized classes that we want to actually play back into the application. And this is tricky because the application may be loading classes from just anywhere. And the way this now works is that you have the situation as follows. So we have some modified class file sitting on disk, and we have the program that is actually using some custom class loader like I showed you, right? So we don't really know what it does. We cannot really analyze the class loader itself. And this class loader is being asked by the program to load some class, for instance, main. And now this class loader loads this class from somewhere, anywhere really. Maybe it even generates this class on the fly, like is done in some programs, right? And the fact is that doesn't really matter to us because now this call is intercepted by the play-in agent, okay? And now the following happens. So we let the class loader load the original class, but just before it's being instantiated, it's intercepted and being sent to the play-in agent. And now the play-in agent looks into its class repository here to see whether it has already seen this class. So it basically tries to do a match to see, do we have a transformed version of this class? And typically this match is done by the fully qualified name, right? So if this class is called foo.bar.main and this is called foo.bar.main, then we have a match. But there are some exceptions. I'll show that to you later. But let's assume we have a match, okay? Then we replace A by the transformed class. So basically that's something that the API here allows us to do. This Java class loading API or instrumentation API. So we basically replace the class's content, literally its byte representation, by the byte representation that we have sitting here on disk. And then this is being passed to the program. So the program thinks it has actually loaded a class from this location here, although that's not actually the case, right? So it was actually loading the class that we had instrumented here on disk. So the play-in agent instantly swaps each class that the program loads for the appropriate class from a given directory on disk. And ideally, there exists a transformed version of every loaded class, right? Then really the complete program will be swapped this way. In the end, you will only be using classes from disk. This might not be the case if the program run that you are executing here, right? So we're talking about an executing program, right? So at runtime, it's loading this class. And if the parameters you're using here for this program run, if they are different from the parameters you used when you actually recorded these classes here with the playout agent initially, then this might cause the problem that here you are actually loading classes that the static analyzer has never previously seen, right? Because you're simply now executing a different part of the program. And then obviously these classes, they don't exist on disk. And then the play-in agent will actually fall back, right? So it will not actually replace the class like I showed you here, right? So it basically the search, it won't find anything. And then it will return the original class that was loaded from here and not the instrumented one, right? So you sort of have to make sure that these runs, they correlate with one another. And we actually saw that this particular limitation can in some situations cause a bit of trouble. So there are a few tricky bits that I still want to explain. So back then, and I don't know, in 2010 or so, we implemented this and we thought, yay, it's working. And, you know, we have some applications, some smaller ones for which the play-in actually works. And we saw that, for instance, we had some optimized classes and now the application was swapping in these classes and it was running a lot faster than it was previously. And we were really happy. But then we saw that for some applications we had problems. And then I looked into the log files and I found entries that look like this. What is this? Well, these are classes that are automatically generated, which in itself wouldn't be so bad. But for some obscure reason, don't ask me why, hopefully there is one, these classes get a randomized class name. Okay, so this is a randomly generated number. It's not securely randomly generated, but random enough so that you know, we can't really easily predict it. And so the problem is we might record these classes and invocations to them during playout, but then if the playout the play-in agent is trying to find a match in the class repository, it will not find a match because in the second run, during which play-in is happening, we might be using different class names altogether, right? So that's really a problem, right? So every time we run the playout agent, we will get new log file entries, right? And for the newly generated class names, and the agent will also dump classes to disk under the new name yet again. So that's one problem, right? So you keep generating classes from run to the next because you think you haven't seen them yet. Although maybe you have seen them yet. You have seen them already, just under a different name. But then we also have this other problem during play-in, right? So you somehow may have the problem that during the first run, you recorded a class that has maybe this class name, and then during play-in, it has a different class name, and somehow you may want to recognize that this is actually talking about the same class, but you can't really match it by name. That's problematic. So the problem is as follows, right? So let's say during playout, we recorded such a class that is sitting here with that name. Now we are loading what is essentially the same class, but under a different name. We won't see a match, and therefore the play-in agent will just forward the original class that was loaded from here, and it won't swap it out by this class. And you know, maybe that's not so much a problem, but if you have an approach that happens to statically optimize classes that are generated with such a randomized name, then this would be a problem to you, right? Because you wouldn't easily be able to swap this out. And as a researcher, I like challenges, so I wanted to solve this as well. And we came up with a solution that almost always works. So the solution is here to normalize the class names. So the idea is that we assign normalized and therefore stable names to classes that are sort of notorious for having randomly generated file name suffixes. Okay, so we have a certain heuristics, basically a certain allow list that is used within Tamiflex to decide whether a certain class name is likely to contain a randomized fraction of a class name, right? And then over this randomized bit, we compute a hash, okay? And then we we compute a hash, not over the randomized class name, that would be bad. We compute the hash over the contents of the class. So actually it's bytecode array because the contents of the class, they are pretty much independent of the class name, right? So they make up, they're made up pretty much of the functionality of the class itself, of its instructions, and therefore this hash is stable. And then the idea is that we replace the random part of the name by this particular hash to normalize it. And then both the play out agent and the play in agent, they just need to use the same hasher component, and then this should work. So let me give you an example. So let's say we have this randomly generated class name here again, and we hash over the contents of this class, then this is the hash, okay? And then we will rename the class to this, right? So this randomized part 1 to 3 will disappear, and we will simply, replace it by this normalized token here. And now this has the following effect. So let's say the playout agent, it records this particular class. Then before we actually dump this to disk, it's passed to the hasher, and the hasher will replace that class name by a normalized one. And now the play-in agent will do the same. So when it loads the same class with the same name, but also the class under a different name, then it will again generate the same hashed name, and it will recognize that particular class, and this can then again be loaded into the virtual machine, right? So we can now generate this match. The problem is, though, that it was not actually sufficient to simply rename the files. The problem is that what I previously explained to you, it's not quite true. So class names are also part of the contents of the actual file. So we also need to rename the class name references inside the class files themselves. And otherwise, actually, also the code wouldn't work anymore. So if you have a class file that has the name A, but it contains a class definition for a file for class B, then the JVM simply won't load it, right? And also for this reason, we have to unify these class names here. And that's relatively easily done, right? So again, we can use the Jumper representation, for instance, to swap out these class names. That's not a big deal. So that's something that can be done. But this actually yielded another problem, because class files with randomized names may sometimes reference other class file with randomized names. And that's problematic because let's say we want to compute a hash for this class. Then in result, we need to replace its class name by a hashed name. But then if this is being referenced by another class, and that also needs to be hashed, then at the very least, if you have cycles between these classes, that's really a problem, right? Because then in order to determine a hash for one class, you need to know its contents, but you don't know its contents before its class name has been replaced. And then you basically have a circular dependency. So let me show you a simplified example where you have no such circular dependency. So here the normalized name of this class depends on its hash code and therefore its contents, but this is actually referring to this other generated class, and this exists, unfortunately, right? So there are generated classes that have references to other generated classes. And so if we normalize this class here, then this will change the reference to this class within this class, right? And therefore also the name that is, hashed for this particular class here. Luckily, we found that in practice, there are no cyclic references for generated classes. That might not be true for every application. There might be some obscure class generation mechanism that even does this. So I'm not entirely sure, but we haven't seen it yet in our experiments. And actually also in the last 10 years, I haven't seen this, which is not to say that it doesn't exist, but maybe it's not a big problem. So assuming that this does not exist, then if a class C with a randomized name references a class D with a randomized name, then D does not reference C, right? So we have only a unidirectional dependency, which means we can then construct a dependency tree. And this is what Tamiflex does. It computes the normalized names starting at the leaf nodes up to the root. So in this particular example, we have this dependency, and we would first hash over this leaf node here. So it is a leaf node because itself does not reference a generated class. It only references other classes whose names we know. And then for this, we generate a hash. And once this is done, we have a normalized name for this class, which won't change anymore. And then we can simply dump this class, right? And we can replace that class reference here in the definition of this class. And then we can also hash this class, and we have a normalized name for this class as well. And we can replace that class name too. And in the end, we then dump to disk this normalized class file as well. So you can see it's the 90-10 rule, right? So the last 10% take up 90% of your time. I don't think that was quite the case here, but I can tell you this last bit with the normalization and hashing, it took up a significant time of our research back then. But yeah, I found it highly interesting, and it is a pretty versatile solution that really works in pretty much all the cases that we came across. So to recap, we can use hashing to assign normalized stable names to classes that otherwise would have randomized names. And this allows the agent to re-identify classes over multiple program runs. And because the classes with randomized names can have references to other such classes, we compute these normalized names in a bottom-up fashion in a dependency tree where the leaf nodes have no such references. And this then brings us to the big picture. So this is actually a picture taken out of our paper where you can see the whole thing, how it all works, right? So here we have the play outside with the dumper and actually also a tracer that actually constructs the log files here. We have seen the hasher, which is also used by the play-in agent on the other side. The play-in agent itself replaces classes at load time. And then down here, you basically can use two different paths. You can either use a Tamiflex aware static analyzer, such as we have implemented it in Suite and Spark, or alternatively, you can use the booster, which gives you these enriched class files that have basically information about the reflective codes embedded directly into the bytecode. And then this can be given to NX static analyzer. So this I should maybe tell you again. So all these transformations that are described here, they are all done entirely on bytecode or on Gimple. So there's no source code required for anything of what we do. You can apply this to any program that is only available in bytecode format. And I think that's also a pretty nice property that really makes this a rather versatile solution. Then in the last video of this week, I still want to talk about experiments and the results that we obtained. I'll see you in a bit.